Our universe is a vast and mysterious place. From exploding stars billions of light years away to the subatomic particles that make up our bodies, the cosmos is full of wonders that continue to amaze and challenge our understanding. But what if I told you that the key to unlocking these cosmic secrets lies in a single elegant theory? A theory so profound that it has revolutionized our understanding of the universe and everything in it. This is the story of quantum field theory. Quantum field theory, or QFT for short, is a branch of physics that seeks to understand the universe at its most fundamental level. It is a world where particles pop in and out of existence, where empty space is teeming with virtual particles, and where the very fabric of space-time is a seething froth of quantum energy. It is a world that is both strange and beautiful, familiar and utterly alien. But don't let the strangeness fool you. QFT is not some esoteric theory that has no bearing on our everyday lives. On the contrary, it is the foundation upon which our modern understanding of the universe is built. From the smallest atom to the largest galaxy, QFT provides the framework for understanding the fundamental building blocks of nature and the forces that govern their interactions.
To understand QFT, we must first journey back in time to the early 20th century, a time when physicists were grappling with a series of baffling experimental results that could not be explained by classical physics. The classical world was a deterministic one where the future could be predicted with absolute certainty if one knew the initial conditions of a system. But the quantum world was proving to be far stranger and more unpredictable. One of the key breakthroughs of this era was the realization that energy, like matter, is not continuous, but rather comes in discrete packets called quanta. This revolutionary idea, first proposed by Max Planck in 1900, marked the birth of quantum mechanics. Soon, other physicists, including Albert Einstein, Niels Bohr and Werner Heisenberg, would build upon Planck's work, developing a new framework for understanding the behavior of matter and energy at the atomic and subatomic levels. One of the most bizarre aspects of quantum mechanics is the idea that particles can also behave like waves. This wave-particle duality, as it came to be known, shattered the classical notion of particles as tiny billiard ball-like objects, replacing it with a more nuanced view where particles could exist in a superposition of states, simultaneously behaving like both a wave and a particle.
Quantum mechanics provided a powerful new framework for understanding the behavior of matter and energy at the atomic level. But it still lacked a crucial ingredient, a way to incorporate Einstein's theory of special relativity, which describes the relationship between space, time, and motion. This is where quantum field theory enters the picture. QFT takes the principles of quantum mechanics and applies them to fields. But what are fields? Imagine a calm lake. Now imagine dropping a pebble into the lake. The pebble creates ripples that spread outward, disturbing the surface of the lake. These ripples are analogous to fields. In QFT, every type of particle is associated with a corresponding field that permeates all of space and time. For example, the electron has an electron field, the photon has an electromagnetic field, and so on. These fields are not just abstract mathematical constructs, they are real, physical entities that carry energy and momentum.
Over the course of the 20th century, physicists developed a comprehensive theoretical framework known as the Standard Model of particle physics. The Standard Model incorporates the principles of QFT to describe the electromagnetic weak and strong forces, three of the four fundamental forces of nature. It provides a remarkably accurate and consistent description of the behavior of subatomic particles. At the heart of the Standard Model lies a bestiary of fundamental particles, each with its own unique properties and interactions. These particles can be broadly classified into two categories, fermions and bosons. Fermions, such as electrons and quarks, are the building blocks of matter, while bosons, such as photons and gluons, are the force carriers that mediate interactions between fermions. The Standard Model has been incredibly successful in explaining a wide range of physical phenomena, from the behavior of subatomic particles to the properties of stars and galaxies. Its predictions have been confirmed by countless experiments, cementing its status as one of the most successful scientific theories ever devised.
One of the most intriguing predictions of quantum field theory is the existence of antimatter, For every type of particle in the Standard Model, there exists a corresponding antiparticle with the same mass but opposite charge. For example, the antiparticle of the electron is the positron, which has the same mass as the electron but a positive charge. When a particle and its antiparticle meet, they annihilate each other in a burst of energy. This process is the ultimate demonstration of Einstein's famous equation E=mc2, which states that mass and energy are equivalent and can be converted into one another. The existence of antimatter has profound implications for our understanding of the universe. According to the Big Bang theory, the universe began in an extremely hot, dense state and has been expanding and cooling ever since. In the early universe, matter and antimatter would have been created in equal amounts. But if that's the case, why do we observe a universe dominated by matter? This is one of the biggest unsolved mysteries in modern cosmology.
Quantum field theory is not just a theoretical curiosity. Its principles have led to a wide range of technological applications that have transformed our world. One of the most well-known examples is the laser, which relies on the quantum mechanical phenomenon of stimulated emission, where photons interact with atoms to produce a coherent beam of light. Another important application of quantum field theory is in the development of superconductors, materials that can conduct electricity with zero resistance at extremely low temperatures. Superconductivity is a macroscopic quantum phenomenon that arises from the collective behavior of electrons in a material. Quantum field theory also plays a crucial role in our understanding of nuclear physics, condensed matter physics, and other areas of modern physics. Its principles are essential for understanding the behavior of matter at extreme temperatures and densities, such as those found in the cores of stars and in particle accelerators.
One of the most counterintuitive aspects of QFT is the idea that empty space, or the vacuum, is not truly empty. Instead, it is teeming with virtual particles that pop in and out of existence, constantly being created and destroyed. These virtual particles are not directly observable, but their presence has measurable effects. For example, the existence of virtual particles can explain the Casimir effect, a force that arises between two uncharged, conducting plates placed very close together in a vacuum. The Casimir effect is a purely quantum mechanical phenomenon that arises from the fluctuations of the quantum vacuum. The quantum vacuum is one of the most mysterious and intriguing concepts in modern physics. It is a realm where the laws of classical physics break down, and where the very nature of space and time is called into question.
Despite its remarkable success, the Standard Model is not the final word in our understanding of the universe. It does not incorporate gravity, the fourth fundamental force of nature. Furthermore, there are several unexplained phenomena, such as the existence of dark matter and dark energy, that suggest that our current understanding of the universe is incomplete. Physicists are actively searching for a more fundamental theory that can unify all four forces of nature into a single, elegant framework. One promising candidate is string theory, which proposes that the fundamental building blocks of nature are not point-like particles, but rather tiny, vibrating strings. Another promising avenue of research is loop quantum gravity, which attempts to quantize space-time itself, viewing it as a network of interconnected loops. Both string theory and loop quantum gravity are still in their early stages of development, and it remains to be seen whether either of these approaches will ultimately lead to a complete and consistent theory of everything.
Quantum field theory has come a long way since its humble beginnings in the early 20th century. It has revolutionized our understanding of the universe, from the smallest subatomic particles to the largest cosmic structures. And yet, despite its remarkable success, QFT is still a work in progress. Many mysteries remain to be solved, such as the nature of dark matter and dark energy, the origin of the universe, and the unification of gravity with the other fundamental forces. As physicists continue to probe the universe at ever-increasing energies and with ever greater precision, we can expect QFT to play an even more central role in our quest to understand the cosmos. The future of QFT is bright, full of promise and the potential for groundbreaking discoveries. As we delve deeper into the quantum realm, we can expect to uncover even more surprises and wonders that will continue to challenge our understanding of the universe and our place within it.
This is just a glimpse into the fascinating world of quantum field theory. I encourage you to explore further, to delve deeper into the mysteries of the quantum realm. There are countless resources available, from popular science books to online courses that can help you on your journey. So go forth, explore, and never stop questioning the universe around you.